So it's my pleasure to introduce Peter Moomin. Peter Moomin had his PhD 10 years ago at both Louvain in Belgium and Delft University, together on the topic of flow into porous media and hygromechanic couplings in porous media, including cracking and hard coupling between the hydric part and the mechanical part. He was a searcher both at ENPA and at ETH Zurich. And 5 years ago, we were glad to have it as a full professor at University of Po. So this guy from the flat country is now lost in south of France and near the mountains, and change his perspective. And now is implied in the topic of micro tomography, and he is head of mixed unity of service. I don't know if it's correct in English, but designs a platform which has a large capacity in material and which is at the service of the community, the overall scientific community of University of Po, but also of partners outside the university. And okay, so we are glad to listen for his conference for about 50 minutes. Thank you, Peter.
Thank you, Christian. Thank you to all of you. I'm actually very glad to be here. When people start giving an introduction about you, you're always like setting the expectations pretty high. So I'll try to live up to those expectations. The subject today is X-ray imaging, and I'll show you some examples that apply X-ray imaging to a subject that's very close to E2S, Energy Environment Solutions, the project in which the university is very active now. So I assume I started from the idea that most of you don't know X-rays. So, but it's not so complicated. Actually, you all know a lamp, I guess. So if you have a lamp, what can you do with it? Well, you can switch it on, for example. And then you're not surprised that there will be light. There is light. Light is an electromagnetic wave, and light is transmitted through materials that we classically call transparent materials. It's transparent because visible light goes through them. And visible light is blocked by other materials that we started calling opaque materials, non-transparent materials. So that's something we're all familiar with. But if you look at X-rays, it's exactly the same thing. You also need a lamp, a kind of X-ray generator, an X-ray source. And when you switch it on, then X-rays are leaving this device. So it's not like radioactivity or something like this. There is really an on-off button, and when you switch it on, then X-rays are leaving this machine. And these X-rays, just like visible light, they're an electromagnetic wave. And the only difference, well, you can see it on the screen here. The only difference is that the fluctuations, they're actually much more rapid. You have shorter wavelengths, and that gives X-rays their penetrating power. So X-rays will not only go through materials that we call transparent, but it will also go through materials that we classically think of as not being transparent at all. And that's a property that people are using every day, actually. If you recently went on holiday somewhere, or you went to a conference or whatever, probably you took a plane and your luggage was checked. So they check in your luggage whether there are fluids there, then there is the customs officer that is saying, why you forgot your toilet bag, whatever. So that is, or if you try to take weapons with you, it's also not a very good idea. So that's X-rays. And the other thing is, if by accident you went skiing this winter, you broke a leg or an arm, you probably had some X-ray scan taken. And also there, well, you can see the inside of a human body without the need to cut it open. a very good property, and now we're not really surprised, but imagine about 120 years ago. It's not such a long time ago. Then a doctor, what did he do? Well, you came there with your problem. He had to remove a tumor, for example. Well, he didn't have any means to look inside, so it hurts at one spot, so he just starts cutting at that location, and then he gradually evolves to figure out where the problem really is. And you immediately notice that that's not really a strategy that is, let's say, adapted for survival. It's not really a good way to do things. So, but that's only slightly more than a century ago. It's not so long. So to imagine this time before X-rays existed. And that time, well, I would like to start this story in 1850. So 150 years ago, 170 years ago in the meantime. Then there was a guy, a German guy, Heinrich Daniel Ruhmkorff. And this German guy, he produced or he patented an induction coil. You can see it over there, an induction coil. What is it? It's just two electrodes, and there is an electric arc going from the left to the right, from the cathode to the anode, they say in the scientific literature. So he was not the inventor of this type of device. Actually, the inventor, that was Nicolas Callan, something like 20 years ago, 20 years before him. But he was just a very good guy he was good with his hands, and he produced these devices, but with very good quality. And so everybody thought he was the inventor. So that actually proves that you don't need to invent something to to get your name attached to some object. Anyway, so electricity didn't really exist. So electricity existed, but they didn't really know what it was. And here, suddenly you see electricity in the air. That's very good, because then you can start investigating this. But it's electricity in the air. So that means that somehow the air also impacts what you're observing. And there was another guy, again a German guy, a few years later, Heinrich Geissler, who invented the Geissler Tube. And what is the Geissler Tube? Well, it's a glass tube, not more than that. It's a glass tube which, and you can create a vacuum inside this tube. And then what can you do with it? Well, you can first of all dim the lights, then you can connect one side of the tube to one part of your generator, and then the other part to the other part of the generator. And suddenly, this electrical spark, well, normally we accept that this electrical spark would happen inside of this tube, but there is no spark anymore. Suddenly we have a glooming light. And Geissler, he was a poor scientist. We all know how salaries in the academic world are. So he immediately saw some potential. He said, well, if I can create color with this, a colorful lamp-like thing, then if I change the gas, for example, the color will change. And so his next trial was this guy. It's very funny, and he thought, well, okay, if I can make this, then maybe this, and this, and this, and this. And then he started his own company, so a first spin-off, let's say, and he started selling what was then known as the Geissler tubes. And you all know these type of things. I mean, the lighting, maybe here not, but in many of the old theaters, it's still this neon lighting, the regular tubes, the white ones. Same principle. So that was invented by this guy. And if you go out tonight, it's Valentine's Day today, you will see this kind of illumination somewhere in bars, Happy Valentine's Day, we love you, Daddy, this type of things. Well, still same principle, so still existing today. But anyway, that's, let's say, we don't want to get sidetracked. What people were really interested in was, we now have this glooming light, but what can you do with it? I mean, what are the properties of this light? And so people started seeing, well, is light, is it maybe magnetic? So they put some magnet close to the light, and yes, this beam is actually moving. Now we know it's actually electrons that run from one side to the other side. Electrons have a charge. If you have a charge in a magnetic field, then it will deviate. But the way that, or the fact that they discovered that they could steer this beam, people that were born here before 1990, let's say, they will remember that a television set more or less had the same depth than it had width. Now it's like this planar stuff, but at that time, it really had some depth. It's this thing, actually. It was like a cathode ray tube. It's one of these tubes, but just in a different form, where you had two sets of magnets, let's say, to steer the beam and to draw things on the screen. And that with a refresh rate of a few tens of hertz, and you had television. First black and white, later color. So again, an invention, neon light first, now television sets, that was all, they all emerged in a very short time frame, 1850s, 1858. One annoying thing, this light, it's produced inside the tube. So if you want to check some property of this light, you basically need to put your measurement object inside the tube, which is vacuum. It's pretty complicated. So it would be nice if you could be able to make this light leave the tube so that you can really touch it and you can start experimenting with it. So that was what Philipp von Leonhardt, again a German, what he tried. And he first tried with transparent coatings and whatever didn't work. And then he had the idea of putting an aluminum, a metal window in there. And metal, for some reason, was completely transparent to this light. They didn't understand why, but anyway, that's not the point. They put a metal window, and suddenly this beam could travel a few centimeters in the air. And so then you could take a fluorescent screen, you could hold it close to it and see the intensity, for example, of the beam. If it glows a lot, it's very intense. If it doesn't glow at all, then it's a very weak beam. So that was easy. And now it's time to introduce, let's say, the main character of today. This main character is called Wilhelm Conrad Rntgen. This guy was, he had a Dutch mother, a German father. He first lived for a while in the Netherlands, went to school there. Then some of his classmates made an ugly drawing of one of his teachers. Then they thought it was him. He didn't want to tell that it was the other guy. He was expelled from school. So, little problem. Then he wanted to go to university, but he had a very bad reputation. So the only thing he could do was actually move, change country. So he went to Switzerland. The only university that accepted him at the time was ETH. Well, now it's known as ETH. Before it had another name. So there he was accepted, did some studies, became a mechanical engineer, then moved a bit around. He went to Strasbourg, went to Germany, went to different universities, until at one point he ended up in the University of Würzburg in Germany. And like many of the people at the time, he was studying these tubes which gave light and where there were beams inside and nobody understood what was going on. So he studied that, and he had the idea on one evening on the 8th of November 1895, he had the idea of doing an experiment. He took one of these tubes, electrified it, looked that it was really glooming, because if it was glooming, that means it works. Then he put a cardboard box over it, and then he switched it on again. And then normally, no light should leave, because that means that the cardboard box is really closed. One problem. Very far in his lab, in a corner, there was something glooming. Meters away. And he knew light can only travel, this type of light can only travel a few centimeters in the air. Here it was meters. It was not even straight in line with the experimental setup. So he thought, well, strange. So next thing, he switches off the generator, glooming stops. Switches it on, glooming starts. Switches off, on, problem. He knew that there was something going on, because if you want an object that it starts moving, starts to glow, there must be some energy transfer from his experimental setup to this glooming panel somewhere. So that's when he started, well, you can verify in your calendars, the 8th of November, 1895, that was a Friday. So he had the entire weekend. He locked himself up in his lab, and he started experimenting. He put this fluorescent screen in light of the tube. He started putting objects in between this light source and the fluorescent plate. And he saw that these rays, these unknown rays, they go through any object. And just if the object gets denser, then there is more shadow. And in lack of a better name, he said, well, okay, for now, for the time being, I'll call them X-rays. If you remember high school mathematics, X was a symbol of unknown. He didn't understand what was going on. And while he was playing around with the X-rays, he put some samples in the beam, and he discovered that, well, he could see his own skeleton. Then he called his wife and said, well, hey, have a look what I'm working on. So please put your hand here in the beam up, and took a picture of it. So this was actually the very first X-ray that was taken. And his wife supposedly was very scared, and she said something like, well, I've seen my own dad. Because obviously, if you see a skeleton at that time, well, it means that you weren't too alive anymore. So, Rntgen, working secretly, working weekends, nights, days, all the time. And he was, in the beginning, very afraid of what his colleagues would say. And in the end, he was really convinced that he really was onto something. And he presented after only 2 months of research, not even, he presented a paper, which you see there, über eine neue Art von Strahlen, is about a new kind of rays. So a new type of rays, the X-rays. He presented this, and the community, they were excited because it was something, but they were also a bit skeptical. And then what they did was, well, everybody was working on these glooming tubes. So everybody went back to their lab, and they just put a tube in, and they repeated the experiments of Rntgen. And one by one, they were convinced, like, yeah, it's true what he says. It's really, yeah, there is some kind of ray. And so from that moment on, everybody became enthusiastic. Rntgen himself, he got in 1901, he got the very first Nobel Prize in physics for exactly this discovery. And because there was so a dramatic potential for these X-rays, they pushed him to take a patent. But he said, no, I mean, this is a technology that can help people. I refuse to patent it to make sure that everybody actually can benefit from it. And so 6 months after this discovery, there were already X-ray scanners in use in hospitals, in Europe, in the United States. They were already doing radiation of tumors. So it's really from discovery to implementation, you have 8 months. It's really almost nothing. Obviously, they weren't aware of all the side effects, and so there were quite a number of problems that emerged later. Anyway, in the beginning, it took quite a while to take an X-ray, 20 minutes, 40 minutes. Then the cameras got better, the sources got better, and they could start to make like these X-ray movies, and they could see how swallowing, how that works, how muscles were used during swallowing, or they could see a beating heart, or they could start to do in vivo experiments on living objects. There is, however, one thing that isn't too clear on these images. Imagine you're a doctor and you get a person who is shot. You take an X-ray, you clearly see the bullet, but at which depth? I know it in horizontally, I know it's on the right side of the person, I know it's about mid-height, but how deep? Well, the solution was pretty simple, but it took a while before they knew. You just turn the person 90 degrees, and then you see the depth. So by combining images taken from different angles, you actually can know the position of any object in space, in 3 dimensions. So from then on, they started developing not just radiography setups, not just pictures, but they started to make 3-dimensional models of the object, in this case, a human body. If you are the person that was shot, probably you just want to lay down. You don't want to do too many things. So in that case, the X-ray scanner, it consists of a source and a detector, and they're just rotating around the person that is just laying down. If you're in a lab and you look not at persons but at objects, it's much easier to turn around the object and to keep the source and the detector stable. But essentially it's the same thing. You look at an object from different angles, you combine all this information, and you get an idea about the 3D object, so 3 dimensions in a non-destructive way. So nowadays, it's the same technology. It has evolved, but it's the same thing that we do. So an X-ray scanner nowadays looks like this. At the left, you see an X-ray source, still a tube inside, still electrons that shoot from a cathode to an anode, still a target that then produces X-rays. And those X-rays, they go on this picture from left to right. In the middle, I'm holding a sample that you position. That sample will rotate to get images from different angles. And on the right, you now see a camera that is a little bit more sophisticated than the cameras at the time of Rntgen, but in either case, it's the same technology. And with a lab setup like this one, this is one that we have in our lab, you can do quite a lot of things. You can look at samples, at materials, you can look at vegetal materials, at plastics, at composites, but you cannot do everything. For example, if you want to be very fast or you need specific properties of very high resolution, then you essentially need to go to high-end facilities. And here's an example of the city of Grenoble. You notice a river, and in between the arms, the two arms of the river, but there is a strange circular building. It has a diameter of, I think, 150 meters or so. It's a pretty large building. And that is a synchrotron. Synchrotron is actually the same thing than we have in the lab. It's just much more powerful. Here you see an image of what it actually is. So you have a huge ring. In this ring, you have an electron beam that is circulating at almost the speed of light. And then you have these gates where X-rays can leave. And when the X-rays leave, they first pass through a hutch where you can tune the properties of the beam. Then you have a small experimental hutch where you put your sample, tiny sample, which you can rotate, again, to look at it from different sides. And you have a control room where you steer all the parameters of your acquisition. Synchrotrons, you have about 50 of them worldwide. In France, it's pretty nice. You have two. You have the European synchrotron facility in Grenoble, and then you have one in Paris, which is called Soleil. So close to Saclay. Anyway. So that's X-rays and the tools you need to produce them. What most of us are interested in is in what you can actually do with them. And all of you, on a daily basis, you actually come across applications that use X-rays. Any household appliance, any object that you buy, basically has been checked by means of X-rays, because you can do non-destructive testing. So here you have an image of a plastic connector. It has 4 pins, and the top 2 pins, you see that there is a wire. They're connected by a wire. Here, clearly the wire is missing. If you need to test every one of these objects manually, just by checking whether there is a connection between the left and the right, would be a tremendous job. Here, it's just passing in front of a camera, and it's scanning in batch mode, and you have this. So it's for your iPhone, for any household appliance that you have, non-destructive testing is used. Food, I guess you all eat. Food is also checked, whether it's canned food, whether it's food trays, whatever. So for example, if you want to eat ragu, you buy this can with ragu, but you don't want to have the bones in there. So they pass by every of these canned food, they check whether there are still some bones left, and normally those cans, they're eliminated. Obviously, the scanning is not perfect, so from time to time you will see some. If you buy cherries, well, they will see whether the stones are in there, yes or no. So, other application, if you like to go to a museum or you're an archaeologist, you discover a great mummy somewhere, you don't want to cut it open to see whether Tutankhamun is really inside. You put this mummy, you put it inside an X-ray scanner, and you will see what is in there. In this case, it's an example of a snake mummy. Or if you have an expensive painting like the Mona Lisa, you don't want to remove the top layer of paint to see which picture is below it. So here is an X-ray scan of the Mona Lisa, and actually it's not of the Mona Lisa, it's of the first drawing of the Mona Lisa, which is underneath the current painting. So you see that X-rays, they're actually used in many different areas. The examples that I chose to show you are all related to energy and environment. As you might know, there was a climate conference in Paris in 2015 where the leaders of our countries, they decided to cut down the emissions of basically all sectors to make sure that global warming, so the average temperature rise on the planet, would remain below a 2-degree level compared to pre-industrial levels, and if possible, even below 1.5. If we don't do anything, well, that's too harsh. If we continue business as usual with the policies in place, then we would head for 4 degrees. So the difference between the blue scenario and the yellow-greenish scenario, that's what we need to realize. It's a huge and aggressive reduction. So if you want to do that, that's not sufficient that, let's say, France says, or the University of Po says, hey, we will become emission neutral, energy neutral. Doesn't work. It's actually all sectors combined need to do efforts. And for every one of these sectors, they looked at what's the potential. What's the potential to reduce energy, to reduce emissions? And for some sectors, well, they're already quite well developed compared to their potential. 40% for the industry from 100% that they could do. Other sectors, like the building sector, they're now at, let's say, 20% of the 100% they could do. Why one more than the other? Well, building stock is usually very old. We have buildings for quite a long time, so many of the buildings that are still existing, they date from technology of 1970s, 60s, 50s, so you're stuck with this heritage. Anyway, all these sectors, there is a huge potential to be realized, and so there are many research projects related to that, and I'll show 4 of them, which are basically spread over these sectors. The first one is the Orchids Project. It was, the principal investigator was Jean-Philippe Thoré from the LFCR laboratory, and there were a lot of other, it was a huge collaboration with an industrial partner, with other labs involved. We had a very tiny part of this project. The global idea here is that industry is responsible for, let's say, 27% is the number that is shown here, but depends on the source, depends on the area, depends on the territory. But anyway, roughly 1/3 of the emissions industry. You can cut down emissions, but you cannot cut them down to 0. There will always be some emissions. Cement industry is very hard to decarbonize. Other industries, same problem. So the idea is to capture those emissions, capture carbon, to use it if possible, and if not, to store it somewhere in a safe underground deposit. That's a system or a technology that is called carbon capture, utilization, and storage. But how do you capture carbon? It's not that you find some molecule carbon here. Yeah. Doesn't work. So you need some specific technology. And in the Orchids project, the idea was to use Clathrates. Now, before Jean-Philippe Thoré came to me, I didn't know what a Clathrate was. So a Clathrate is like a chemical substance, like the picture on the top right there. And if you give it a specific arrangement, then it forms a kind of cages. And these cages, they have the right size to host a molecule of a gas. Here, these green dots, they represent molecules of a guessed gas. And so the product or the Clathrate that he was interested in was HQ, hydroquinone. And HQ exists in different forms. One of the forms is the alpha form, and in the alpha form, it's like a nice crystal. It's like a quartz crystal, so it's nice, it's translucent, but for every 18 HQ molecules, you can only store 1 gas molecule. So it's not really efficient. On the other hand, if you take this, if you take the same material, but you just rearrange the dots, then you end up the beta form. It's a bit uglier, I would say. It's not translucent. It's a crystal, huh? But in that way, for every 3 molecules of HQ, you can store 1 guest molecule, which is a pretty high ratio. It means that you can really store a lot of gas in this thing. The only question is where and how. And so what we did was taking one of these crystals in its original shape, alpha form, and then expose it to carbon, CO2, for a long time, 30 days, at more or less ambient temperature and slightly elevated pressure, 3 megapascal. And you just wait. So you have this crystal, it's exposed to the gas, You wait, you wait, you wait. And then you pick out your sample again, your crystal, you put it again in a tomograph, and you can compare the two images. What I hope that you can see is that the image on the left here, well, it's a crystal and it has surfaces which are, let's say, more or less smooth. While the picture on the right, you see there is roughness. It's like, wow, it has been eaten or something like this. It's a bit, well, it's a rough surface. It's not the same thing. So there was something that happened. Now, this is just images. This is a way to, let's say, guess what happened. You can also quantify things. I just show this graph to show you that you can get numbers out. It's not the idea that you understand what's going on here. The bottom line is the pores inside this crystal, they got smaller. But the sample itself didn't change size. And if you want to make sure that these two observations, that they somehow make sense, then you have to propose a mechanism. And the mechanism we proposed was that you have this initial crystal. When it comes into contact with CO2, then this crystal will start swelling because you have these molecules that somehow get inside the grid and they get trapped. And so all the HQ molecules get a little bit further apart, one from the other. So the material swells. But CO2 is also a pretty aggressive environment. So you start eroding the surface, attacking the surface of this crystal. So the outer surface is attacked, but the inner surface remains free. So this explanation is compatible with what we see. But it took 30 days. And in an industrial process, 30 days is way too long to store a couple of molecules of CO2. So the next thing after we understood what was going on was to see how can we speed up this reaction. And different strategies were tested. So first of all, you could, for example, crush these crystals to improve the specific surface. So more surface means faster. That worked, but to some extent. The best way they found was actually you take silicium particles, spheres, and you coat them with this active material, and those spheres, you just stack them in a reactor and you let gas pass by. And you see that then, well, it's just tentative, but you notice that the speed actually increases dramatically, certainly here in the beginning, and you can do this in a cyclic fashion. So this was a project where we went from the very beginning, identifying the mechanism up to the end. Other projects that I will start showing now, they're still ongoing. So the final results, we don't have them yet. So I would like to make a new appointment for another talk in some near future, let's say. Anyway, second project is called RINGS. Principal investigator is Pierre Césac. And here, again, large consortium with industrial partners, different labs involved. I'm not in any way the lead researcher in this project. Tomography is always a small part in every project that I'm showing you. It's about storing gas. I don't know whether you know, but the European Union, they decided, or they wrote something they call the EU Renewable Energy Directive. So, and what is written in that one is that 32% of renewable energy, that we need to have 32% of renewable energy by 2030. That includes hydrogen. And there is a sub-target, 3.5% of advanced biofuels and biogas. Well, a biofuel, that's a gas that results from the anaerobe transformation of manure, crops, all biosubstances. So basically you take biomass, you transform it, and it becomes biogas. And biogas, when you purify it, it's biofuel. It's biomethane, actually. So this biomethane is useful because you can burn it, and then you can heat houses. You can use it as a fuel for cars, or you can generate electricity with it. So many applications of this biogas. Now I need to give you a little bit of context. So you have a producer, NG in this case, produces biomethane. And then there is you on the other side, and you consume methane for biomethane for heating your house. But you will more or less use biomethane in winter and not in summer, while NG wants to produce continuously. So you have this gap between offer and demand. And the only way how you can cover that gap is by storing the excess you have in one season and use that excess in another season. And therefore, a gas transport company like TIGF, which is now called Terega, or like Storengy, what they do is store this excess gas in a subsoil aquifer or a reservoir. They do that for years now, all works fine. But they do that with natural gas. And now suddenly this European Union decides to use biogas. And what does it change? Well, if you take biogas and you look at it under a microscope, you see all these tiny creatures. There are microbes in there. It's traces, it's not much, but there is some life in there. And if you start injecting that into your underground reservoir, actually nobody knows what's going to happen. You don't know whether these animals, let's say, that they're really happy to be there, and so they will start forming biofilms, and so they will clog all the pores that you have, and then you will never get out your gas again. That's a problem. On the other hand, they could change the acidity of the soil, and if they do so, then, well, maybe you will start dissolving, and in the end, well, first permeability increases, and then maybe your gas leaks out, and you lose everything, you cannot get it out. And there are many more impacts that you could have, and nobody knows what's going to happen. So the idea here of this project is really to analyze what's going to happen when you inject biogas into a reservoir. So they is LATEP. LATEP, they developed a test cell which operates under reservoir conditions and mimics reservoir conditions, meaning there is solid, there is liquid, there is gas, there is a water table that can move height, and you would, at some times during the experiment, you would take out samples. And to compensate for the volume that you take out, the volume of this reactor can also change, so to compensate. And we get these samples, well, not only we, there is a huge analytical workflow there behind it, but what we do is looking at them. And what you notice there in gray are the sand grains of this reservoir, and in red are the biofilms. So here, in this case, and these are the preliminary testing, here you see that there is indeed bio growth or biofilm growth, and it's actually blocking the porosity, and mainly in the big pores. That's a preliminary result. In the coming years, we'll get to the bottom of this, and the idea is that in 2021, we're able to tell to these companies, to these transport companies, what the upper limit is of this biogas that they can inject in their reservoir to not have problems. Two more examples, but since they get increasingly more recent, means that we are increasingly less far in the research part. So here, a project related to bioconcrete. It's from LMDC. It's part of the University of Toulouse, and the PI is Camille Magnon. Why looking at the building sector? Well, building sector, I already mentioned it. Much of the building stock is actually pretty old. And if you look at emissions, well, the building sector is responsible for 1/3 of the emissions. It's quite a lot. Some of it during building, but most of it in the materials used for building. So what can you do? Well, first of all, you could recycle existing buildings. And secondly, you could develop new buildings, new building materials which have a lower carbon content. So the idea in this project is that on the one hand, we're in the Aquitaine region. Aquitaine says fields. Huh? There are many fields. There's maize, there is sunflower, there's a bit of everything. And what is useful of maize? Well, it's just a corn, and all the rest is basically waste. On the other hand, you have concrete, and concrete is a material that is used everywhere, but if you don't use like fibers or you don't use reinforcement, then it's actually a pretty fragile material. It cannot take a lot of tension. So the idea is pretty simple. You take vegetables, well, the stem, it's actually fibers. You take these fibers, you mix them into the concrete, you get bioconcrete, and you avoid to use plastic fibers or steel fibers or whatever. That's the idea. So the advantage would be that you have a very low carbon footprint because it's natural resources and you recycle waste, and you have a very good hygrothermal behavior. It's an isolation material, it has a moisture buffering capacity, all properties that we really like. But there are some open questions, namely, how many fibers do you need to add? How good is the connection between the fiber and the matrix? Which orientations do these fibers have when you just mix them in the fluid? Do they have a preferential orientation? Is it a bit random? What happens with this type of new material over time if you use it today but you recycle it or look at it behavior? Building is something that is supposed to withstand for 10 years, 20 years, 30 years, generations. So what happens to these materials? And all these questions, well, not all of these questions, but some of them we can answer with micro-CT again. So here you see a scan of a bioconcrete, and well, it's not the entire bioconcrete, these are all the fibers. Fibers color-coded, every different color is a different fiber. And the picture on the right is a bit difficult, but on the horizontal axis, we show you the orientation of a fiber in a horizontal plane, and on the vertical axis is how much it actually leans. So we basically give orientations. If this graph would be uniform, all the same color, that means that there was no preferential orientation. But here we notice that there are clearly some spots which have a higher preferential orientation, or which have a preferential orientation, and it's all close to zero for the inclination. Or in other words, most of these fibers have the tendency to lay one on top of the other, and so form preferential planes which are orthogonal to gravity. So just it sinks down and it settles down. Next steps in this project are optimizing this mix, optimizing the fiber content, optimizing the connectivity between fiber and matrix to make sure that we have materials that are market ready and have low environmental impact and live up to the expectations. And the last project is about, well, renewables. Well, everybody speaks about renewables. You need solar panels, you need wind, you need whatever. But wind, sun, it's all pretty fluctuating. Mobility, same thing. If you need to store this energy, well, you need to store it somewhere. And usually you store it in a battery. Battery technology, however, is, well, this graph on the, is about the energy. How much energy can you store per kilogram of something or per volume, per cubic meter of something? And so if you look at a gas, well, gases, they don't have a lot of weight, so you can store a huge quantity of energy in 1 kilogram of gas, but they occupy quite some volume. So you have very little storage per unit of volume. So that's why they're not here low on this graph. On the other hand, liquid fuels, petroleum, well, all the jet fuel, diesel, gasoline, LPG, all the fuels that you put in a car or in a plane or in a rocket, they're high up there. Meaning that in terms of weight, they're actually, you can compact really massive amounts of energy in a few kilograms, a few liters. And the density is so high that actually, the gravimetric density is actually so high that it doesn't take too much volume either. So they're excellent. Current batteries, they're here. So in terms of volume and in terms of weight, they're worse than anything that exists. And that's a problem. Because if you want to replace, let's say, jet fuel for a plane with something like this, you need to take a battery in there that is much heavier than all the weight, and if you put that on a plane, the plane doesn't take off anymore. So you need to develop batteries that are much more top right. So lighter, smaller. And if you look at battery technology, the existing ones are these gray ones here. Lithium-ion batteries. That's what you have in your laptop, in your phone, in everything. But you notice that there are other types of batteries around, and they're all being developed. And the class that is more top right is these of the solid-state batteries. What is a solid-state battery? It's a battery without liquid. Everything is solid. So you have a solid electrode, you have anode, solid cathode, solid electrolyte. Everything's solid. So these batteries, they are very promising. Plus, they're very safe. Because you cannot, if you puncture the surface of one of these batteries, there's no fluid that can start leaking out. They're all solid. So it's inherently safe. They're perfectly stable. They have a very long life cycle. They should have low cost. So it seems like the holy grail. But there are some challenges left. And so the idea is to, in a project that is led by Hervé Martinez, it's still under evaluation, so we're not sure we can do this, but it would be very enthusiastic to be able to do this, to look at all the problems we still have with batteries and to make sure that we, by 2024, so in 5 years from now, that we have a commercially available battery that is able to compete with current fuels. What can we do with tomography? Well, our role in that would be we put a battery inside our tomograph, but we put an entire battery inside the tomograph, and then we put loading and unloading cycles, and we see what happens. And we look at this battery at the inside and how actually these interfaces, which are the key point, how these interfaces, how they swell, how they degrade, whatever that is going to happen. So that's what we want to observe. We want to understand the mechanisms, and we want to make sure that we can improve them. There's Arkema and Saftin there who are experts in the field. There's an entire analytical platform at IPREM who is able to do detailed analysis of chemical composition of everything. So that's the next thing we would like to do. So I come to my conclusions. I told you a story about discovery of X-rays and how they were immediately applied in the field of medicine. Then I showed you that X-rays are really not limited to medicine. Actually, they're something for all of us, daily life, food, archaeology, culture, whatever. So you're coming across X-rays all the time. And I also showed you some applications of recent work that we're doing now related to energy problems, storing energy, storing gases, improving capacity of building materials, and so on. All this work, it's not my work. I have to thank some people. First of all, the team. Without them, none of these scans would be done. None of the analysis would be done. So they're great, and so I'm really grateful to work with them. Also, universities, CNRS, Total. Without them, there wouldn't be an environment to work in. And then all the industrial and academic partners, because if they don't come with projects to us, we essentially don't have work. So if you have projects, if this interests you, don't hesitate. If you want to come to work with us, don't hesitate. There are open positions. There is a summer school, so please, you're welcome. And if there are questions, I'm there for you.
Thanks a lot, Peter. It's now open for discussion and questions.
The first question is the hardest.
With X-ray, can you watch fluids or just solids?
You can watch fluids. The only thing is that they shouldn't move within the time that you look at an image. So if they move, your image will be foggy. Just like if you take a movie of, I know, Tour de France is passing by in this region regularly. So if your frame rate is sufficiently high, then you see all these cyclists with very sharp images. If you have a shutter time that's way too long, well, you just have like a foggy flow that is passing by. So yes, we can see fluids, but they shouldn't move too fast. So if you have a fluid inside the porous medium, then usually the flow is so slow that it's not a problem.
And what cannot you see? What is the media that you cannot see with X-ray?
There are very few materials that you cannot see, but the problem is mainly related to the equipment you have. For example, lead, PB. Lead is a material that is extremely dense. And extremely dense materials means that if I put them inside my beam, in our case, if I have 1 millimeter of lead or 3 millimeters of lead, but the beam stops, I don't get photons on the other side. So, it's very visible to me because it will be a huge black spot. But so the problem is more related. If you would have a more powerful X-ray beam, it wouldn't be a problem. And the other end of the spectrum is also hard. So I mentioned biofilms inside porous medium. It's actually a pretty hard problem because the solids, the stones, they're very dense. So you need a powerful X-rays to get through them. But the biological material, well, it's carbon, it's very soft tissue. So if you have a powerful beam, it doesn't feel the presence of this carbon. So you actually need a low energy for the carbon, but you need a high energy for the stone. So you need to devise acquisition methods based on multiple energies to make sure that you get good quality images.
You must be able to capture a low variation of energy of a large amount of energy.
Yeah, so you need very low or high signal to noise scans, otherwise you're lost.
So if you have a porous medium with some fluid inside the pores, you cannot see both because the energy,
yes, you can.
The energy should be calibrated on something, either on the solid mass or on the fluid mass.
You can see both, and you can see them at the same time. The only thing you have to be careful is that if their densities are too close to one another, then their gray levels will be the same. And if you have two gray levels that are too close, where close is defined based on the noise you have on your images, if it's a very sharp image, then, well, low noise image, then the smallest step you will see. But if you have some noise in your images, and you always have noise in your images, then as soon as your densities get too close to one another, you essentially don't see the difference anymore. But a fluid and a solid, normally one is, let's say, water is 1,000 kilogram per cubic meter, a stone is 2,000, so you have a factor 2, it's sufficient.
Thank you.
Sorry, I have a specific question. How did you separate the fibers that were stick together?
How did you separate the fibers? So we're speaking about these biomaterials. Normally the fibers, they have a different density than the matrix around it. And so how do we, okay, that's a pretty tricky question. So, okay, I was about to answer to say, well, how did you separate the fiber face from the, let's say, the matrix face? So then you split things into two groups. This is fiber, this is matrix. Her question is, well, okay, now you know you have this blob of fibers. How can you actually chop it up into individual fibers? That's the question, no? It's pretty hard. So either the easiest way to do it, I would say, is to, there are operations which are called erosion. So you actually reduce the surface, you reduce one by one, you remove voxels, or voxels are pixels in 3D, one by one up to the moment you have like the median line. And at some point they will start to be separated one from the other. Then you know how many objects you have, and you can use that information to start splitting. So that's one strategy. Other strategies would be that you use some a priori information that you say, well, a fiber is always an elongated object, so I'm going with some kind of deep learning strategy. You start looking for elongated objects and you chop up into elongated objects. But in both cases, you need to play a lot. There is no magical recipe. You need to play a lot to make sure that you get them separated. And the human eye is really perfect. So if you think that it's not good, then don't trust your computer.
Yes, actually, I have a question related to computers, actually, and machine learning. You were mentioning deep learning, and how today, because I don't really know the progress in this area, how the communities are working together with deep learning or any kind of machine learning, artificial intelligence to perhaps to improve the way to interpret the image, or perhaps the way you are taking the image or the precision that you are using, the speed. I don't know how these two worlds are working together, if you have an idea.
It's a very good question. We are only at the very, very beginning of this. But it is a very hot topic in the field of image analysis. just like it is a hot topic in the field of signal analysis. So I can tell you what is now that in commercial software that is now appearing, so the current versions, some deep learning algorithms start to be increasingly present, which is usually an indicator that some research is mature enough to be included in commercial codes. I can give you one example. It's Dragonfly. It's a free software for academic users. I don't have, let's say, shares in this company, so it's just free information. But Dragonfly, the current version, has a deep learning module, and that allows you, on the one hand, for example, related to the previous question, if you want to do segmentation. Segmentation is separating in different phases. Then you can, the human eye, I mentioned it already, is very good. So you take a little part of your image and you show the computer like this is really fiber, this is really matrix, this is this, this is this. And then it will learn based on this information and apply it on the rest of your sample. You have other deep learning modules that are in there, for example, to remove noise and to improve the resolution. So it will learn about, for example, if you have a material which has spherical pores or whatever, after a while it will, by analyzing just the topology or the texture of your image, it will discover that it's actually spheres. So it will improve the resolution of this boundary, and then you have a better definition. So these type of strategies, they start to be implemented in codes. On the one, that's on the one hand. On the other hand, we always try to push this a bit further, so it's an active research domain.
There is a question on YouTube. So can you see materials under pressure?
Can I see materials?
Under pressure.
And pressure?
Under pressure.
Under pressure. Well, the answer is yes. But you can see materials, and if you want to apply pressure, then you obviously need to put, like, I don't know which context it is, but if it is like a mechanical test, you need to put a press inside your tomographic setup, which needs to miniaturize the setup, but it's possible. And like François Renard already did this. He has a test setup. There is a commercially available test setup produced by Deben. So yes, it's possible. It's called In-Situ Testing. You essentially, that relates to a question by Domenico. Can you see then how the structure is evolving over time when you put it under pressure? And the idea, or the answer is yes, you can see that, but you should adapt the speed of your experiment to the speed of your acquisition setup. So you can put some force, take an image, put a bit more force, take a new image, or you can load very gradually and then take continuous images. In a synchrotron, let's say continuous imaging is going very well. If you do it in a lab setup, I would do the one by one, because that's a much higher chance to succeed. But yes, it's possible. And not only forces, can also be fluids that flow, can be temperatures that change, can be crystals that grow, can be fractures, can be everything.
Merci beaucoup.